myself Prasad Meghavarna. So we are going to start the power systems. So the first topic that we are going to discuss here it is transmission and distribution. So later on power system analysis and later on switchgear and protection will be discussed. So first of all, so we'll start with the transmission and distribution of electrical energy. So we know that for entire power system we are expecting 13 to 16 marks, and out of 13 to 16 marks, so highest weightage will be given to F&S and later on transmission distribution, and least weightage will be given to the economic load dispatch and power system protection, right. But in the recent years somewhat more weightage is coming in transmission and distribution also, right students. See, if you see the syllabus of transmission and distribution, so first of all we are having the basic part, and later on the transmission line constants calculation like resistance calculation, inductance calculation and capacitance calculations, and steady state performance analysis, the most important chapter we can say. So where we have to discuss about the short transmission line, medium transmission line and long transmission line analysis and their ABCD parameters calculation, and along with them we are having lot of concepts in the third chapter, and the next chapter voltage control and power factor correction. It is also one of the equally important chapter like chapter 3, and underground cables, overhead line insulators, corona, so they are least important chapters, and distribution systems also somewhat most important chapter, right. So as we have discussed already, so basic part is very important, and transmission line constants and steady state performance, voltage control and distribution system, these are the most important concepts we can say. Sometimes there may be a chance that they may ask the questions in the underground cables also, right. So whenever you are going for the examination, you have to go with enough concept of the underground cables also. Overhead line insulators is somewhat very easy, corona also somewhat very easy, so nearly half an hour preparation for them. But so underground cables will take somewhat more time, so that so learn with somewhat more concept, right. First of all, coming to the basic part, students. So we have seen the single line diagram of the power system. Coming to the single line diagram of power system, students, if this is the generator and this is the transformer, and here we are having the transmission line, here we are having one more transformer, and here we are having the load, right students. So this is the generator, this is the transformer T1, this is the transmission line, this is the transformer T2, and that will be the load. So we know that whenever an element delivers active power, some positive value of active power, that element is always called as a source. So means the generator is always delivering some positive value of the active power, and the load is always absorbing some positive value of the active power. So any element which takes active power is called as a load, any element which gives the active power is called as a source. The best generator we have preferred is the synchronous generator, The synchronous generator can deliver both active power and the reactive power. So it can deliver some positive value of active power, and it can have delivering capability of reactive power also, or it can have absorbing capability of the reactive power also, or it can have zero reactive power also. So we know that the synchronous machines are having the excitation to control based on the over excitation or under excitation or normally excitation. They can have delivering value of reactive power or absorbing reactive power capability or zero reactive power capability also. And coming to the load always absorbs active power. The best load is the motor we can take, that motor is the induction motor. The induction motor always absorbs some positive value of active power, and absorbs the reactive power also, right students. So a load which always absorbs active power and also it absorbs the reactive power also, not all the loads, only induction motor. but synchronous motor is having excitation to control. So it can be over excited, it can be under excited, or it can be normally excited also. So according to the cost, according to the construction, and according to the application point of view, we have selected induction motor as the best motor. So the best source is synchronous generator, the best load is the induction motor we are having. Students, and here you have to recall one point here called about the operator J. Operator J. So operator J is nothing but it rotates the vector anti-clockwise by 90 degrees. It rotates a vector anti-clockwise by 90 degrees. Means the value of J is under root of -1, that is the mathematical value, and it can be represented as 1 at an angle of 90. 1 at an angle of 90. Wherever J square is there, it will be square root of, so overall square, it will be -1, it will be 1 at an angle of 180 degrees from the reference point. And if you see J cube will be, so minus J, it will be 1 at an angle of -90 or 1 at an angle of 270. Like that you can write. And coming to the J power 4, J power 4 will be J square, which is nothing but 1. It is 1 at an angle of 360 or 1 at an angle of -360 or 1 at an angle of 0. All are same only. Right? J power 4 is J. 1. J power 4 is 1. J is 1 at an angle of 90. And what is the value of J conjugate? What is the value of J conjugate, students? J conjugate is 1 at an angle of 90 whole conjugate. So it will be 1 at an angle of -90, which is minus J. And what about 1 by J? Means J inverse. What is J inverse? 1 by 1 at an angle of 90, which is 1 at an angle of -90, which is minus J. Therefore, J conjugate and J inverse both are same only. Both are is equivalent to minus J only. So these are some points we need. So whenever you are entering into the power system part. Right, students? Now, so we need to know the ratings of the power system elements. So we are having some various power system elements. What are the power system elements we are having here? Generators, transformers, transmission lines, and the loads. So we need to know the ratings of these power system elements. So which are very important. So first of all, how can we give the rating of an element? The rating of an electrical element can be given by based on the losses. The rating of an electrical element. Rating of electrical element we can give. Here, the rating always depends upon the temperature rise. Temperature rise. The temperature rise depends upon the losses. The losses are, one is current dependent, one is voltage dependent. So voltage dependent losses are iron losses and current dependent losses are copper losses. Right? So these are depending on V, these are depending on I. So that VA rating we can give. VA rating. So VA rating means volt ampere rating. Right? So volt ampere rating is nothing but apparent power rating. Apparent power rating. So the power system elements like which elements we are having for generator, transformer and transmission line. For all these elements we have to give the apparent power rating. Sir, why can't load? Means load specifications will be given by the consumer, so that we no need to give the rating for the load. So based on the requirements of the consumer, we have to decide the rating of the load finally. So means which type of loads can be manufactured will be decided by the consumer only. What he needs, that only we have to manufacture. But generators, transformers, transmission lines, all are rated for apparent power rating only. Volt ampere rating or kVA rating or MVA rating based on the size. Right? So less is the size VA rating, more is the size kVA rating or MVA rating we can give. Generally, in our power system, we can give 3-phase apparent power rating, which is in MVA, So generally, if you take for generator, rating of generator means synchronous generator only. Rating of the synchronous generator. So the first rating we can give is 3-phase apparent power rating. 3-phase apparent power rating. So that should be given in MVA. And the second rating that you have to give for the generator is line to line RMS voltage rating. That should be given in kilovolts. Right? So that we have to give two ratings. One is apparent power rating and one is the voltage rating. So wherever you are having the generator like this, if this is the symbol we are using for generator, so for this one, so we have to give suppose 100 MVA and 11 kilovolts. Then 100 MVA will become 3-phase apparent power rating, and this 11 kilovolts will become line to line RMS voltage rating. Right. So strictly speaking, line to line RMS voltage, okay, strictly speaking it should be full load voltage, right? So we can say line to line full load RMS voltage rating we have to give. That is the voltage rating of the generator. And similarly, the next one we can give is the power plant, the rating of the power plant. Rating of power plant. Rating of power plant. In power plant or generating station, we are having several parallel connected generators. Like that we are having the generators. These may be having different power ratings. It may be 100 MVA. This may be having 200 MVA. This may be having 50 MVA. They may be having different apparent power ratings, but they should have same voltage rating, right? Means all are having 11 kilovolts, 11 kilovolts, 11 kilovolts, then it is 11 kilovolts bus, right? So that definitely one generator rating is the rating of the power plant. Whenever you are giving 3-phase apparent power, that is line to line full load RMS voltage rating, that voltage rating will be the rating of the entire power station. But one more rating you have to give. While giving the rating of the power plant, the rating of power plant will be decided by the rating of the turbine which is driving all this, all the generators. Means rating of power plant is nothing but rating of turbine. So rating of turbine means we have to give 3-phase active power rating. 3-phase active power rating. Right, students? Therefore, the two ratings that you have to give is, first one is 3-phase active power rating. That should be given in megawatt. And second one is line to line full load RMS voltage rating. It should be given in kilovolts. Right, students? That's why wherever we are having generator bus, so this bus we can call it as the generator bus. So where we know the value of active power P and the voltage V. That's why generator bus we can treat it as PV bus. So wherever P and V are known, that bus we can call it as the generator bus, right? This is the rating of the power plant or rating of the generating station. Next one is rating of the transformer, which is a shunt device. Rating of transformer, right? So here first one is 3-phase apparent power rating, 3-phase apparent power rating, which should be given in MVA, and second one is voltage rating. For transformer we have to give two ratings, primary voltage rating and secondary voltage rating. So primary no load voltage rating, secondary no load voltage rating. Line to line, primary no load, it's not full load, it's no load. Voltage rating in kilovolts bar, line to line, secondary no load voltage rating, actually RMS voltage rating, which should be given in kilovolts. So both primary and secondary no load voltage ratings we have to give, right? Right. Therefore, whenever you are having a transformer like this, for transformer, whenever you are saying 100 MVA, 11 kV bar, 33 kV, then this 100 MVA will be 3-phase apparent power, and 11 kilovolts bar 33 kilovolts, both are line to line voltage on primary and secondary. So V line primary bar, V line secondary. So we know that transformer is the only shunt element, and transformer is the only element which is rated for no load voltage. Remaining all power system elements are rated for full load voltage only to reduce the overall cost. But there is no chance to give full load voltage rating for transformer. Why? Because it is a shunt device. So because of that one, we have to give default the no load voltage rating only. Right, students? That's about the rating of the transformer. And coming to the next element, transmission line, rating of the transmission line. Rating of transmission line. In case of the transmission line, same 3-phase apparent power rating, 3-phase apparent power rating in MVA, and second one is line to line full load RMS voltage rating. It should be given in kilovolts, right? So wherever we are having a transmission line like this, suppose if they are saying it is 100 MVA, 100 MVA transmission line means that is the 3-phase apparent power rating, yes, 3-phase, and suppose they are saying it is 66 kilovolts transmission line. For 66 kilovolts transmission line, this is the line voltage, full load line voltage, like that we can give. So almost all the power system elements, generators, transformers and transmission lines are rated for the line voltage. That's why in case of a 3-phase power system network, the rated voltage means it is line to line RMS voltage. Maybe full load or no load, that depends upon the particular element. But what is the rated voltage of power system means, we can say line to line RMS voltage, right? So we can say, therefore, the rated voltage of power system we can say 3-phase power system is line to line RMS voltage, line to line RMS voltage. That is the rated voltage of the 3-phase power system. And coming to the last element, load. So we told already load will be given by the load rating will be given by the consumer. So consumer needs more glow from the bulbs, more air from the fans, more cooling from the refrigerators. So that's what he need. So that all more glow from bulb means more wattage, more air from fan means more wattage only. So that any load always represented by the wattage. So more the wattage, more will be the output that you are going to get from that particular load, right? So you can say rating of load. Rating of load. So for this load, first rating is 3-phase active power rating in megawatt, and second rating is operating condition. So operating condition means operating power factor, or what is the reactive power required to produce this much or to convert this much amount of active power into useful form. Useful form means we know that we are giving electrical energy to the load. For a motor, for example, for a motor we are giving, for a fan we are giving electrical energy. So what is the output of that one? Useful form of air. How much air it is going to convert. So that depends. That depends on how much electrical input it can take, that much amount of output it can convert. But while converting that, how much amount of reactive power it needs, right? So that we have to represent here. Operating power factor, operating power factor, or 3-phase reactive power rating. So we should be given in MVAR. That's why. So for a load, we know the value of P, we know the value of P, and we know the value of Q. That's why. So wherever you are having load bus, wherever you are having load bus, which can be represented as a PQ bus. It's a PQ bus, or simply called as a load bus in the load flow analysis, we can say. Generator bus, PV bus, load bus, PQ bus. They are the only two buses we should have, but one more extra bus is also there, that we will discuss in the later classes, right? So these are the ratings of all the power system elements, right students? Take this one. The total reactive power supplied by the mission 2 will be, mission 2 will supply how much amount of reactive power? It may be supplying to mission 1 or it may be supplying to mission 3, doesn't matter. Finally, how much it is supplying? That's what the question. That's what the question. See the question clearly. Mission 1 is 120 at an angle of 30 degrees, and here it is J1, it is 100 at an angle of 0, it is minus J1. Mission 3 is 200 at an angle of 30. So now they are asking what is the total reactive power supplied. It may be positive or negative. Positive or negative. Why? Because sometimes mission 1 may be supplying reactive power to mission 2. Under that case, it will absorb. In some case, mission 2 may be supplying reactive power to mission 3. Compare both. Finally, so how much it is going to supply totally? Right? Try to calculate that. How much amount of reactive power will be supplied by mission 2? So first of all, calculate the current here. Let us assume any random current direction. This is I1, this is I2. These are the two current directions we have assumed. Calculate current I1, calculate current I2. Right? From I1, calculate complex power absorbed by mission 2. From I2, calculate complex power supplied by mission 2. So we can write here the current I1. What is the current I1 is equivalent to? 120 at an angle of 30 minus 100 at an angle of 0 by J1, 1 at an angle of 90. So this will be 120 at an angle of minus 60, 100 at an angle of minus 90. Where I1 conjugate is nothing but 120 at an angle of 60 minus 100 at an angle of 90. complex power absorbed by mission 2, S absorbing, which is nothing but S2, which is V2 into I1 conjugate. So where V2 is 100 at an angle of 0 into I1 conjugate. So 120 at an angle of 60 minus 100 at an angle of 90. So it will be 120 into 100, 12,000 at an angle of 60 minus 10,000 at an angle of 90. This is S2. From this one, so we don't need active power. Directly I am calculating the reactive power. Q absorbing, Q2 is equivalent to 12,000 sin 60 minus 10,000 sin 90. Can you tell me this value, students? Make it fast. I am calculating only reactive power. There is a chance that they may ask about active power values also. Here it is, whatever it is required, I am calculating that. 12,000 sin 60 means root 3 by 2. 6,000 root 3 minus 10,000. 6,000 root 3 minus 10,000. 392.3. 392.3. 392.3 where it is absorbing power. So mission 2 absorbs, but they are asking delivering quantity. One more current you can write here, I2. So this value minus this value divided by this impedance is the current I2. You can write current I2. It is 100 at an angle of 0 minus 200 at an angle of 30 divided by 1 at an angle of minus 9. It is 100 at an angle of 90 minus 200 at an angle of 120. What is I2 conjugate? It is 100 at an angle of minus 90 minus 200 at an angle of minus 120. Now I am calculating S delivering, the complex power delivered by mission 2. Complex power delivered by mission 2. Why it is delivering? Current is leaving, source notation. Why it is absorbing in this direction? Current is entering, that's why load notation. For load notation, we are absorbing, we are calculating absorbing quantity in first loop. In second loop, current is leaving the second mission, that's why we are calculating the delivering quantities. For the same mission, we are calculating both absorbing and delivering now, right? See here, S2 is equivalent to V2 into I2 conjugate. It will be V2 is 100 at an angle of 0 into 100 at an angle of minus 90 minus 200 at an angle of minus 120. Multiply here, it is 10,000 at an angle of minus 90 minus 20,000 at an angle of minus 120. So we need to calculate Q delivering value, Q2. How much it is? 10,000 sin of minus 90 minus 20,000 sin of minus 120. Can you tell me what is this value? 7320. Positive or negative? Positive only, na? Positive only. 7320.5 where. So total delivering is this one. Out of that we have to remove how much it is absorbing. How much it is absorbing, right? So therefore total delivering will be, therefore Q2 total delivering, it is 7320.5 minus how much it is absorbing, 392.3. 392.3. So what is that value? 6928.2. 6928.2. Like that you can calculate. It's one of the simple problem only, but the way they are asking the questions, so you should be ready for that one. They may ask about the active power, they may ask about the reactive power, they may ask about the polarities also. Based on polarities, we have done many problems in the class. Yeah, almost all the students are having more clarity how to identify the polarities, right? So that's why I have taken one problem based on the numerical. In classroom, we have not done the numerical. We have done the problems based on only polarities, right? One more extra way, they may ask the question. So this is the way. You should be ready for this one also. Highest level you can expect. Why? Because they may ask this type of questions for only 1 mark only, right? 1 mark, this much lengthy means highest level we can say. They don't give this type of questions for 2 marks. 2 marks, right? Why? Because all are very easy calculations only, right, students? That's about the single phase power transmission case. And coming to the 3-phase power transmission, in case of 3-phase power transmission, we are having 2 sequences. One is positive sequence and one is the negative sequence. So 2 sequences we are having. Positive sequence means ABC, negative sequence means CBA, and or we can say ACB. So whenever ABC is the positive sequence, when A is reference, when A is reference, ACB will become the negative sequence. So here we are having 2 types of connections. One is star connection and other one is the delta connection. So 2 types of connections we are having, star connection and delta connection. So in case of star connection, the line voltage are root 3 times that of the phase voltage and leads the phase voltage by 30, and line currents are exactly equivalent to the phase currents. And in case of delta connection, the line voltage and phase voltage both are same only. If you want to say that phase voltage should be the line to line voltage of the star connection. The line to line voltage of star connection is nothing but the phase voltage of delta connection. I never say that phase voltage of star is the line voltage of delta, means that's wrong. Line to line voltage of star is the phase voltage of delta connection. And the line currents are root 3 times that of the phase currents and lags the phase currents by 30 degrees. This is what we are having in case of both star connection and delta connection. In any connection, the power is always, so the active power 3 phase, it is V phase I phase cos phi 3 times, right? So here also P 3 phase, it is 3 times of V phase I phase cos phi. And in terms of line quantities, it is root 3 times of V line I line cos phi. Here it is also root 3 times of V line I line cos phi. This is what we have studied in the 3-phase basic part, right? Now we'll take one problem based on this one. Try to give me the answer for this one. What is the value of ZBC, the impedance ZBC, to have IA plus IB plus IC is equivalent to 0? So what is the value of ZBC? So how much impedance we have to place here to have IA plus IB plus IC is equivalent to 0? See the question clearly. Very simple question only. The value of ZBC to have IA plus IB plus IC is equivalent to 0 will be. Simplest way is, first of all, convert delta to star. Right? So one thing is missing here, voltage. Voltages are not given while typing. The voltage they will give here. VAN is equivalent to 100 at an angle of 0. VBN is 100 at an angle of minus 120. VCN is 100 at an angle of plus 1. For that voltage, calculate the impedance. Voltages are not typed here. Line to neutral voltages are given, but the connection given is delta connection. That you have to understand here. So simplest way is convert delta to star, delta to star, or otherwise convert this voltage into line voltage. Anyone you can do. So we need delta to star transformations here. Whenever you are having delta connection like this, so we have to convert this into star. So this is AN, this is ZAN, this is ZBN, this is ZCN. So they have given it is ZAB, ZBC and ZCA. So what is the value of ZAN? What is the value of ZAN? Can I write it as ZAB into ZCA divided by ZAB plus ZBC plus ZCA? Is it correct formula? Is that correct formula to write ZAN? Delta to star transformations. Is that correct formula or not? Right. So similarly, ZBN formula you can write, ZCN formula also you can write. So substitute the value of ZAN formula, ZBN formula and ZCN formula. Right. And after writing the values, they are asking IA plus IB plus IC must be equivalent to 0. IA plus IB plus IC must be equivalent to 0. So here the only variable is ZBC, na? What they are asking? ZBC. Here also only variable is ZBC, here also only variable is ZBC. Where IA is nothing but VAN divided by ZAN plus VBN divided by ZBN plus VCN divided by ZCN. All are is equivalent to 0. VAN, VBN, VCN values they have given. In all the three formulas, ZAN, ZBN, ZCN, in all the three formulas, only unknown quantity is which one? ZBC. Substitute that and then calculate the value. And then calculate the value. Right, students? This is the other way of asking the same question. Already we have done this type of question in star. Right. So now they may ask the question in delta and may ask the similar type of quantities. ZAB is 5, ZBC unknown, ZCA is minus J10. Substitute all the values and solve it for ZBC. Solve it for ZBC. Will you solve this one? I have given the idea. Just I have given the idea. So try to solve this one. In ZAN formula, ZBC is unknown, ZBN formula, ZBC is unknown, ZCN formula, ZBC is unknown. Right? In all the three cases, ZBC is unknown. Right? So solve for ZBC. Solve for ZBC. Equation, closed loop equation you have to get. In terms of voltage also you can get. Right? And what about the closed loop equation? IA plus IB plus IC is equivalent to 0, they are saying. Right? But how can you write the equation there? IA is nothing but IA is not is equivalent to VAB divided by ZAB. That's wrong answer, right? Remember, students, sir, can I convert this phase voltage into line voltage? He is asking. Can I write IA is nothing but VAB divided by ZAB? That's wrong. IA is nothing but VAB divided by ZAB. It's a wrong conclusion. You should never get like that. Always you have to do the calculations in phases and then you have to convert into the line quantities. Somebody done the calculation, very good. 29.28 at an angle of minus 210. 29.28 ZBC at an angle of minus 210 degrees. 8.27 at an angle of 84.44 degrees. Right, I have not solved for the value, right? We need to solve for that value. Just check it. I will also check that one. 29.28 or 8.27. So only the magnitude they are asking. Only the magnitude. Right. So please go through the calculations perfectly. Right, students. So this is the way. This is the one more way. You should be ready. You should be ready. So there you may be doing the mistake like this. That's a wrong way. Sir, IA plus IB plus IC means line current is nothing but line voltage divided by line impedance means that's wrong. Always you have to do the calculations in the phases and then convert into the lines only. Right. That's all. That is the only important point you have to remember here. Right. That's about the three-phase power transmission, students. So single phase power transmission problems and three-phase power transmission problems, these are the ways they may ask. You should be ready where, in which area. So particularly calculation of impedances, in star connection or delta connection, these type of problems are very, very important, right? And in single phase, so these are the most important problems we can expect from chapter 1. And coming to the second chapter, transmission line constants calculation. Transmission line constants. Transmission line constants means we can say RLC, resistance, inductance and capacitance are the calculations. So resistance is nothing but rho L by A, generally we can take rho L by A, generally we can take. And whatever the skin effect we are having, that skin effect we are going to consider in the transmission line constants. Students, in chapter 1, we have not studied about the classification of conductors, right? Solid conductor, ACSR conductor, AAC conductors, all those things I am not giving here. Why? Because those are not that much important for gate examination, right? So if you want to learn, just go through skin effect, right? So remaining concepts are not that much important for the gate examination, right, students? Classification of conductors, type of conductors, all those things are not important there. So directly I am going for the next chapter. R is equivalent to rho L by A. So whenever you are taking AC conductor, it is A dash you can write. So resistance of AC conductor is always more than that of the resistance of the DC conductor. That is because of the skin effect, right? And coming to the inductance calculation, L is equivalent to 2 into 10 power minus 7 ln of GMD divided by GMR, Henry per meter. Or it will be 0.2 ln of GMD divided by GMR, millihenry per kilometer. The inductance of a single conductor. So whenever you are going for inductance of the loop, it will be 2 times 0.4, right? So inductance of the loop or inductance of the single conductor, that depends upon, right, what they are asking. Inductance of the circuit also sometimes they may ask. Right, students. Now about the capacitance calculation, CAN is equivalent to 2 pi epsilon naught into epsilon r divided by ln of GMD divided by DS, where DS is similar to that of GMR without 0.7788 farad per meter. So we are having different configurations here, symmetrically placed configuration, unsymmetrical configuration, like that we are going to have. For all the configurations, GMR, GMD calculations are very, very important, right? So we'll take one problem here. For example, just one for example, we'll take find the GMR of the configuration. I will give like this. The radius of each conductor is 1 centimeter. What is the value of GMR, students? So that is the bundle conductor they have given. For that bundle conductor, what is the value of GMR? Just for recalling only. Any answer? So GMR means first one, second one, third one and fourth one. D11, D12, D13, D14. So how many distances? 1, 2, 3, 4. 4 distances, fourth root you have to take. So it will be fourth root of D11. It is 0.7788 into R. R is 1 into distance from 1 to 2, 2R. Distance from 1 to 3, 2 root 2R. Distance from 1 to 4, 2R. They are the radius, right? So it will be fourth root of 0.7788 into 1 into 2 into 2 root 2 into 2. It will be 1.732 centimeters. 1.732 centimeters. Like that you can calculate, right?